All right, this is going to be the second video on chapter 15 on equilibrium. And this time, so the last example that we left off with was we knew what the equilibrium concentrations were, so all we had to do was plug them into my equilibrium expression. Now in this problem, they have given me initial concentrations, and I can only plug them into my equilibrium expression if they are equilibrium concentrations. So in this place, what we're going to have to do is we're going to set up what's called an ICE chart. And ICE stands for Initial Change Equilibrium, ICE. And we're going to put our reactants and then our product. So I've given the initial concentration. We were also supplied with the initial of the I2, and we didn't have any of the HI. They did, however, give me the equilibrium concentration of HI. So if this starts at 0 and at the end we have 1.87 times 10 to the negative 3, then I know what my change is going to be. So my change is going to be plus 0.187 times 10 to the negative third. Now that means this had a coefficient of 2, so these would be half of that much. So they get the same change, but it's cut in half because they don't have the same coefficient. So now we would do 1 minus this to get the equilibrium and 2 minus this to get my next equilibrium. So now I have all of my equilibrium concentrations, and I can plug them into my equilibrium expression and find my equilibrium constant. Now, sometimes they don't give me any equilibrium ones. They only give me initial ones. So when we are calculating that, when we put in initial values, it's called Q, which is called the reaction quotient. So it's not the equilibrium constant because we're not equilibrium. It is whatever our conditions are at that time, and it's Q. And it's going to look the same as K, except it's Q, and we just put in our current conditions, not necessarily the equilibrium ones. Now, if Q equals K, then I'm at equilibrium. If Q is less than K, then my reaction is going to go forward. And if Q is greater than K, then the reaction is going to go in the reverse. All right, so if we've been given our initial amounts, we're going to do it in an ICE chart, just like we did before. So for this particular one, they tell me I have a 1 liter flask, I have 1 mole of H2 and 2 moles of I2. So then my concentration would be 1 divided by 1 and 2 divided by 1. So those were those. And then I didn't start out with any of this. So that means it has to go forward, because if I were to calculate Q, it would be 0 over this stuff, which would be 0, and Q would be then much less than K, because K was 50.5. So since my change is going to be minus x, because I don't know what it is, and this one is plus 2x, because I'm using these up if it's going forward, and this has a coefficient of 2, that's why it's 2x. So 0 plus 2x is 2x, 2 minus x is 2 minus x, and 1 minus x is 1 minus x. So now we're going to plug these equilibrium concentrations into my equilibrium expression. So those are the concentrations I had. I'm setting it equal to K, and I'm going to do a quadratic equation, and I'm going to get 2 roots. So anytime I do the quadratic, I get 2 roots. Sometimes one of them is negative, sometimes one of them is positive. In this case, they're both positive, but only one root will work. And you're saying, well, how do I know? Well, in this case, I have 1 minus x. So x can't be 2.3. That means I would end up with a concentration that was negative, and that's not possible. So that means that this 0.935 has to be the correct root. So that means H2 is going to be 1 minus that number. I2 is 2 minus that 1. And then we said HI was 2 times x. So now I know all of my concentrations at equilibrium. Now the next part of this video is going to be on LeChatelier. And LeChatelier says that if I have a system at equilibrium and I disturb that system, the system then is going to shift either toward the products or toward the reactants in order to undo that shift. So you're saying, well, how do I disturb this? What are these stresses that I'm going to put on there? And we're going to look at 3 of them, and those are changes in concentration, changes in pressure, or changes in temperature. Any of those are going to affect the direction of my equilibrium. Okay, so if I am at equilibrium and I add a reactant, the reaction is going to say, no, I don't like this. I don't want that. I want to get rid of it. So I want to figure out which way I'm going to remove that reactant. So in order to remove the reactant, it's going to shift toward the products in order to use up that reactant. Okay, if we have gases involved, then we look at pressures. Okay, and if we have a change in pressure or volume, because pressure and volume are inversely related, then if we have a higher volume, that means we're going to have a lower pressure. So if we would happen to lower the pressure, we would want the pressure to go back up, do the opposite to undo that. And that means we're going to go to the side that has more moles of gas, because if we have more moles of gas, that's going to create a higher pressure to undo that lower pressure. And finally, changes in temperature. And changes in temperature, it depends whether your reaction is exothermic or endothermic. If your reaction is exothermic, then the heat is on the product side. If it is endothermic, then the heat is on the reactant side. So in other words, if my reaction goes forward and it's exothermic, that means when I go forward, it makes it hotter. If it's exothermic and I go reverse, it makes it colder. And in an endothermic, it would be opposite. Reverse would be hotter, forward would be cooler. All right, and lastly, a catalyst. So a catalyst, all it does is make the reaction go faster, but the forward reaction goes faster, and so does the reverse. So that means that it doesn't change the position of the equilibrium. It's not going to shift one forward or reverse. And this always seems confusing to students because they're like, if it doesn't do anything, then why do they ask me? Well, every textbook for some reason seems to ask this question just to mess you up. So if it says a catalyst is added, that does nothing. There is no change in the equilibrium. It's not going to shift forward or reverse. All right, so here is a practice problem. So there is my equation, and it tells me delta H is 58. What that means is this is a positive value, so this reaction is endothermic. So I'm going to put over here, if it's exothermic, then heat is on the reactant side. All right, so it says in which direction is the reaction going to shift if I add N2O4 and if I do all these things. So first we're going to look at N2O4. So if I dump more of N2O4, the reaction is going to say, no, 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 I don't want that. I want to get rid of it. So to get rid of it, I have to go to the right in order to make more products and use up that extra reactant. So shift to the right. If NO2 is taken away, so if I take some of this NO2 out, the reaction says, no, 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 I want that back. So to get it back, again, it's going to want to shift to the right in order to make more product because I took it away. The next one is the pressure is increased. So if the pressure is increased, we need to lower the pressure. This side of the reaction has 2 moles of gas. This side of the reaction has only 1 mole of gas. So if I want to reduce the pressure, I need to shift to the side with fewer moles of gas, which is going to be shifting left. And if the volume is increased, that means the pressure is decreased. So if the pressure is decreased, the reaction says, no, 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 I want the pressure to go back up. So in order to make the pressure to go back up, I have to shift to the side with more moles of gas, which would be shifting to the right. And finally, the temperature is decreased. So in this reaction, since it's endothermic, hot is on the left, colder is on the right. So if I decrease the temperature, it says, no, 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 I'm too cold. I need the temperature to go up. So in order for the temperature to go up, I have to shift to the side that makes it hot, and that would be the left. All right, and this would just summarize the stuff that we went through. So that is going to be our last video, the last section for this chapter.